we will talk about the theory of chemical reactivity. Okay. Now, when you talk about the theory of chemical reactivity, within a density functional theory framework, that particular branch of DFT, as it deals with concepts related to reactivity, this is called conceptual DFT. When you talk about the concepts, in chemistry there are several popular qualitative chemical concepts. Okay. And just simply analyzing various chemical reactions and the trends therein, several concepts are developed and there are associated electronic structure principles also. So, you have heard like concepts like electronegativity, hardness, electrophilicity. Now, these are the concepts which have been in the chemistry literature for ages, but they are mostly qualitative in nature. Now, the attempt was that whether we can provide some kind of theoretical rationale or background for those qualitative chemical concepts and the associated structure principles or not. Then you will see that how the conceptual DFT developed. So, when you talk about reactivity, now you have to start from the very beginning. Do you know what exactly do you mean by reactivity? We say that this molecule is more reactive than that molecule. What does it mean? How do you measure that reactivity? So, first you have to define what do you mean by reactivity within, let us say, a quantum mechanical framework. So, now let us go back like what I told yesterday, that the Hamiltonian remember, I will start from the scratch, that if I ask you that you represent a molecule or an atom or whatever quantum mechanical system, the only information you know about that system is its Hamiltonian, nothing else. Okay. If you get the Hamiltonian, you can construct its Schrodinger equation. If you are lucky, you can solve it, get the wave function, from there get all other properties as the expectation values of the corresponding operators. Or in DFT also, somehow you have to know the Hamiltonian. And another thing we have shown for this type of many electron systems, say particularly we are talking about molecules in this case, let us say, your Hamiltonian operator depends on two quantities. Okay. N and Vr. If you know N and Vr, N is the number of electrons, Vr is the external potential, means external potential of the electronic problem is the electron nuclear attraction, and you can add other, say you place the molecule in some external electric field, magnetic field or whatever, or you can think about some fictitious reaction field. So, solvent, heat bath, anything which is external to your electronic system. If you know these two, you can completely characterize the Hamiltonian. That means these two quantities, they will totally fix the Hamiltonian. You won't have to bother about anything else. And also, you can see your DFT also started like this, that if you know the density, can you get N and VR? Then we are assured that we know Hamiltonian, wave function and all other properties. N we get through simple integration, a quadrature, and VR we have seen that in principle you can do through a reductio ad absurdum proved by Weinberg and Kuhn. Okay. So now let's start with this. So reactivity is like related to reaction. Reaction means you have some action and how, what is the response of the system? You are doing something, system is responding. That is its reactivity. So first thing you have to identify, what do you mean by the action? Then only we go for the reaction. You have two handles now, two knobs which you can operate to perturb a system. Okay, that means now I am telling my action is del N del VR. So what does it mean? That suppose you have a molecule or any such many electron system, it has to start with let's say some number of electrons, and it is experiencing some external potential due to the presence of the nuclei or other say potential fields. I add some electron to it. I take out some electron to it. What is the response of the system? That is your del N. That is my action. I am perturbing my system. So you want to see if you have some action, what is the reaction? And that reaction, nature of the reaction will tell that is the reactivity of the system. So now you can see that reactivity, which was otherwise a very, very qualitative concept, we are trying to give some kind of say mathematical flavor at least to the concept of reactivity. So we are developing gradually the theory of chemical reactivity. So you have change in the number of electrons, or you can change the external potential. External potential means what? Suppose I have a nuclear framework. The nuclei, they are doing vibration, rotation, translation of the whole molecule. What is the net effect on the molecule and how it is reacting back due to that action? So these are the two ways you change delta N or VR or both. Okay? And then see what is the reaction. For this, we will talk about CDFT based reactivity descriptors. There are two types. One we will call global reactivity descriptor, another we will call local reactivity descriptors. Okay. What do you mean by global reactivity descriptor? Suppose if you have a molecule, you perturb the system by changing N, VR or both. The whole molecule, how it behaves, that will give me the global reactivity of that. But suppose if you want to know in this specific, let's say atomic site or maybe a functional group in a molecule, what is the effect? In organic chemistry, you know that a particular electrophile will attack a specific atomic site in a molecule. So there, the reactivity of the whole molecule is not important. I have to know the reactivity of the specific site. So we have to define another class of reactivity descriptors. They are called local reactivity descriptors. Okay. So how will you define them? So it's a very simple approach. What we'll do, this is a general perturbative treatment. So what we're doing, we're perturbing the system by changing N and V R. Okay. So let's say we start with the molecule where the energy corresponds to a specific number of electrons and specific external potential like N0, V0. Unperturbed system. Be louder.
You mentioned that the VR is changed by translation of a molecule. I didn't get that.
Hmm.
You mentioned vibration, rotation, and translation.
You see, the whole molecule is moving. Nuclear coordinates are changing. They are moving from one place to the other. Center of mass is moving. So if the nuclear positions are changing, electron-nuclear attraction, that would depend on the positions of the nucleus.
But if I am saying molecule, I also need the electronic structure, not only the nuclear.
I think he needs the translation.
You see, I told you yesterday that when we talk about molecular geometry or molecular structure, that is governed exclusively by the positions of the nuclei. Suppose if I ask you, say, ground state geometry of water, you tell it is C2V. How do you know? You simply specify the positions of oxygen nucleus and the two hydrogen nuclei. Do you bother about the electrons when you talk about the geometry? No. Now, when the nuclear positions are changing, it is vibrating, it's rotating, it's translating. Electronic problem is there at the background. For that, in order to solve the electronic Schrodinger equation, you require the external potential. What is the external potential in absence of anything else? It is just the positions of the nuclei which will determine the Coulomb potential associated with electronuclear attraction. Okay. So what are, you think about all possible ways how you can change the nuclear positions. Translation, vibration, rotation, all of these motions, they are basically changing the nuclear position and accordingly electron-nuclear attraction. Okay? You remember, I wrote that it is Z alpha by mod small r minus capital R alpha vector with a minus sign, sum over all sorts of stuff. So if R alpha, that capital R alpha is changing, this quantity will change. That is your external potential, isn't it?
I thought that both the R's are shifted by convolutions. His viewpoint is translational motion should not change the electronic structure.
No, no and no. When you are changing this, the amount of electronuclear attraction is changing. So you are going to a typical non-equilibrium state in relation to the previous equilibrium position where there is no force acting on the system. Now, if you consider, you have to solve again the electronic Schrodinger equation with the new nuclear coordinates to get the new electronic structure or the new electronic wave function that gives you psi star psi will give you the electron density distribution, that is your electronic structure. It will try to go to that stage again with the new nuclear configuration. Still the electrons will adjust so that there is no net force acting on the system. Okay? And it will give you a new equilibrium geometry and new electronic structure. And that's what you have been doing. So when you scan the potential energy surface, you are changing the nuclear coordinates and seeing how the overall potential energy is changing. And remember, in the potential energy, you have the electronic energy embedded, because that's the definition: nuclear repulsion plus the electronic energy, which is the eigen value in the electronic Schrodinger equation. Okay, and that is a function of capital R, because if you change the capital R, the solution of the electronic Schrodinger equation will change. Okay. Do you have any other question before we proceed? Anything else? Okay, so now I want to know what happens to the energy of the system. Say, when I perturb it. So what I do, remember, I am considering the perturbation up to second order, but nowadays there are reactivity descriptors for perturbation up to third order, fourth order, etc. Let's just simple mathematical extension of this perturbative treatment. Okay, but I'm not going into it. The actual idea, if you can understand, that itself is sufficient. So, what happens to the energy of the system when there is some action? Okay, now the number of electrons have changed, the external potential has changed by the amount del n and del v. Okay. So this is a simple Taylor series expansion. plus higher order derivatives are also there. This is a simple Taylor series expansion. Okay. Manoj, this is the beauty of this board. So you can see here what are the say chemical significance of these derivatives, various derivatives. So we will go one after the other. This one, mu, don't bother about this, just remember that the way I am writing. Okay. Just I am dropping the names right now, but I will tell you say physical or chemical significance of this. So the first derivative of energy with respect to the number of electrons is your chemical potential. Second derivative is the hardness. Del E del V R is just the density. Can anyone prove and tell me why del E del V R is rho? Any one of you? DFT is not just pressing a button. You have to know the calculus of variation. How do you get del E del V R equal to rho? Who would be able to tell? Tell. Is it? You see, before I go to other two terms, you remember E rho is remember this is your kinetic energy plus electron repulsion, which doesn't depend on external potential. That's why they say universal functional. This the energy coming from the external potential. Okay, this is the energy functional. Go back. J of y. I am doing this exercise so that you will understand the whole algebra properly. Otherwise, you will just commit to memory. So that I don't want. You know how to derive this. Okay, all the terms you can do it. So J rho A to B F x y y prime dx. Okay. What is del J del y? Fy minus ddx of Fy prime. You can expand it second order, you can go for other number of variables. Simplest possible one I am telling you. Okay? Put it over here. Your J is E, Y is rho. There is no VR over here. Okay? So, derivative with respect to VR is 0 for FHK term, and this is also 0. What about this one? Rho r VR, that is your F. Take the derivative with respect to VR. What do you get? Rho of r. This is your rho over.
Can I make a point? Slides are being here. That is, although one says that FHK is independent of VR, when you change V, you also change rho. When you change rho,
I'm talking about the perturbation up to this order. So higher order,
no, that will be first order itself. Because that will be del F, del rho, del rho, del V. So best is, for this case, best is to go to first order perturbation theory of quantum mechanics, and that's the best way to do it.
yes,
Because in that case, what will happen, you take the, even if you do that, chi rho, I r r prime integrates to 0, that's why the second term gives.
yes, yes.
But in principle, one should write that so that there's no confusion.
No, but I'm talking about simple definition of the functional derivative.
Sir, could I ask you to elaborate? I was asking the same question.
What?
What did you
So
say?
we can keep these questions, we can do it in the discussion in the afternoon, evening when I come.
I was asking the same question that rho should in fact be a functional of V. So if we change V, so we should be using chain rule of differentiation here and should take the differentiative of derivative of f with respect to rho.
You see, when we prove the Weinberg-Kohn theorem, obviously rho and V, they are interdependent. But when we say that rho fixes the external potential, that means we are not considering that changing rho will changing V. That thing is not there. I am considering one rho relative to one specific V. Okay. So in this case, I will assume that when we are doing the variation of V, the associated variation in all other properties. So if you change V, sometimes it knock out an electron also. Do you consider that also as the variation of V means change in N? No. Okay, we are considering the first order derivative, but it is functional derivative. Another thing, if I ask you now, del E del rho, let's say, what will be del E del rho? From here itself, you tell me. No, because here explicit rho dependence, Manoj, explicit rho dependence is there. So if I write del E del rho, del E rho del rho, it gives you VR plus del F HK rho del rho, and this is nothing but your chemical potential. This is your Euler-Lagrange equation, remember.
No. In this case, when you do del E del rho, you have to the external at the bottom.
Which one?
The external, del E del rho here, so you are keeping V fixed. That's how the variation.
Yes. Yes.
V has to be kept fixed.
Yes.
Similarly, when you
So that's why I am putting here VR constant, here N constant, and that is the way the Taylor series expansion is written of two variables. So you can see this is nothing but your Euler-Lagrange equation. Okay. So unless you don't know how to calculate the functional derivative, you won't be able to proceed. So here you can see the Euler-Lagrange equation, del E del rho is the Lagrange multiplier mu, and that is nothing but your VR plus del F HK rho R. Now any DFT treatment you go, depending on how do you choose your FHK, you will get a specific Euler equation. One specific case is your Kohn-Sum equation. Okay. So there you choose FHK in terms of, let's say, non-interacting particles and get sum over I minus half del I square sort of stuff, so that you can reduce the many particle problem into single particle orbital based framework. Okay. So that is a specific form for FHK, where FHK you can choose some density based, proper density based one and get a single density equation, or let's say orbital free DFT. That depends on how you define your FHK. And that is the whole of DFT about, choosing different FHKs, nothing else. So starting point is the Euler-Lagrange equation, which tells that you are minimizing energy, which can be written as a density functional, and the density is normalized. That's it. Okay. So this is your density, and I did something byproduct also for mu, that I can connect this mu. I will show how you can connect that with this definition of mu. This is called Fukui function, which I will come back later. And from here you can see there are two different definitions possible for the Fukui function. Okay, this is the cross derivative. So we will check this cross derivative when we go to the local descriptors. So these descriptors you can see, this is a global descriptor because it doesn't vary from point to point in a molecule. It is also a global descriptor for the whole molecule. This one varies from point to point. So this is a local descriptor. At a given point, what is the value? This one also at a given point, what is the value? Here it is the 2 points. See, what is the value at this point as well as at that point? Together, we can define this. They are called linear response function. Okay. This one is your Fukui function. This one is your linear response function. So, global descriptor, reactivity descriptor. First, we will talk about the first order derivative. This is the first order response. This is a chemical potential. But you remember, I have taken a different definition over here. Here it was del E del rho, here is del E del N. Let's see. So mu from del E del rho here, that's your simple Euler-Lagrange equation gives you. Now here, N is what? So can you tell what would be del N del R? Functional derivative. A derivative with respect to y. So this gives you 1, isn't it? It's the derivative of this with respect to rho r. So this gives you just 1. Do all of you understand? Just fy minus ddx fy prime, no fy prime here. Fy prime comes where you go to say GGA, meta GGA, their first order, second order derivatives all come. But here, it's, let's say I am writing only in terms of density. So f derivative with respect to y will give you just 1. You have to take the derivative of rho with respect to rho, this 1. Okay. So this quantity is 1. So you can see this is the definition what I have used during perturbative treatment. Okay. So a new definition of chemical potential I am deriving as del E del N. Okay. Because your functional derivative etc. that's very complicated stuff. So here we are doing it as a del E del N, and that tells the how energy changes if you change the number of electrons. First order. Now, say you are changing number of electrons at constant external potential. Then you are not disturbing the nuclear coordinates, okay, or you are not putting any external bias. So, in this case, how the energy will change? Let us see. There are variations where you can change some fractional number of electrons also at different finite temperature concept, but I am not going into that. Standard chemistry stuff, add one electron, take out one electron, like this. So, my delta n can be +1, -1 of that type. Okay. So, E n plus 1 is E n plus similarly, I can do it for E n minus 1 . Huh?
Delta n is -1 anyway.
What?
Second equation.
Huh?
Delta n is -1, so you should keep that plus. Delta n is -1,
I am taking n minus 1.
so that would remain plus.
N minus 1, the first order would be negative. Oh, that is the standard.
Delta n is -1, so it will not be negative.
No, no, I am considering delta n 1.
Okay, write that down.
Yes. So, I have to treat them in the same footing, otherwise two different delta n values will not do. Okay. So, first let us do 1 minus 2. 1 minus 2, what do you get? I am doing simple algebra. In conceptual DFT, you have functional derivatives, etc., but mostly I will be doing addition and subtraction. Finite difference analog. Okay. So, what do you get? E n plus 1 minus E n minus 1 is twice mu delta n. Okay. This gets cancelled, this gets cancelled.
Actually, if you take delta n as -1, now this then hardness part will be. That is how hardness comes as n plus 1.
Yes, yes.
It may be easier if
Whatever way you do, you get the same result.
that part will be.
Yes. So, I will do that just next moment. Okay, so you see this is the mu delta n. So, mu delta n plus mu delta n twice mu delta n. So, delta n if I take 1, so my mu is E n plus 1 minus E n minus 1 by 2. Okay. So, you can tell me anyway what is the big deal. Del E del n, this is the simple finite difference analog, is A n plus 1 minus E n minus 1 by 2, isn't it? So that's what I have done. Now, add and subtract En. What is this quantity? Approximately, I am telling. En plus 1 minus En. What is that? Electron affinity, or negative of that. Okay. What is this quantity? Ionization potential. That means you get this is minus A plus I by 2. Okay. So now you can see that chemical potential I am writing in terms of some experimental quantities like ionization potential and electron affinity.
Some problem. You are writing En plus 1 minus En minus 1. Then you are putting minus En minus En. So this would actually, you understand what I'm saying? There is some problem. Actually this should be plus.
No, it's okay. It should be plus right here. En minus 1 minus 1.
This one.
Yeah, because you're getting plus En minus 1 here.
Correct.
Plus En plus 1
So
minus
you make it plus here.
That's it.
But then,
Yeah,
then it is okay. Because minus A minus C. This will be minus I, this is minus C. Then it is perfect.
Yes. So now you can see that we are writing this in terms of some experimentally observable quantities like ionization potential and electron affinity. But this I plus A by 2, it was already just prescribed by Mulliken that this quantity is the measure of electronegativity. This Mulliken's electronegativity is I plus A by 2. So that means what I can see that chemical potential is just the negative of the electronegativity. And this electronegativity is called absolute electronegativity. You remember, when I talk about the electronegativity of the molecule, generally we have to tell that which particular partner it is coupling with, so that you can talk about its electron transfer direction, etc. But here it is telling, forget about anyone else. This is for the whole molecule. That's why they are called absolute electronegativity. Okay. So mu, 1 minute.
Since we are fixing the nuclei, should we call these as vertical ionization energy, vertical electron, something like that?
Yes. We are actually always, that is positive point as well as negative point. Positive point in the sense that when you do the calculation, like if I want to calculate En plus 1, En minus 1 for delta SCF type calculation, I don't have to do the geometry optimization. I will do single point calculation. Okay, I have to calculate, suppose you have a neutral molecule, I will calculate a cation and anion, En plus 1, En minus 1. And for doing this, whatever geometry I optimize for the neutral system, I do a single point calculation just by adding an electron, and single point calculation just by subtracting an electron without doing any geometry optimization, because VR is constant in the definition. Okay. So no geometry optimization, so no relaxation, etc. when you add an electron. Okay. So it measures basically if you have a molecule you consider is a reservoir of electrons, and the electrons electronegativity will tell you that the chemical potential basically tells you how facilitated it would be so that the electron can move from that. So, this is what is called the escaping tendency of the electrons. So, chemical potential becomes a measure of the escaping tendency of the electrons. Okay. So, you get the first order derivative like this. What are the second order derivative? You simply again another finite difference analog will come. You do 1 plus 2. What do you get? Tell me. If you do 1 plus 2, and you remember this one is your hardness. So, what do you get if you do 1 plus 2? No. What is the formula you are getting? And take delta n equal to 1. You tell me when to stop. No. We will also tell conceptual DFT. Huh? No. I am telling I will go up to 10:45 because I started late. Okay. So, what do you get? Eta? You are getting I minus A, isn't it? So mu part will cancel. And you get again the finite difference analog. You know that second order derivative is what? Say E n plus 1 minus 2 E n plus E n minus 1 by delta n square. Okay, there is the second order derivative if you write in the finite difference analog form in the numerical analysis. So, you get straight away that, and that is nothing but your I minus A. I cannot hear. No, actually, if you just excite an electron or if you add an electron, whatever you do, ultimately what is happening? It must change, say, whole electronic setup. But if you assume that as if it is just taking out one without considering any kind of relaxation or whatsoever, then what he was telling, you get that. And because your external potential is constant, you are permitted to do that. Remember. So, if I do E n plus 1 calculation, that is the let us say calculation of the corresponding anion with the neutral molecule geometry, so it saves my computer time. So, instead we are doing a single point calculation, not geometry optimization. That I think we will discuss later. No, here when we talk about let us say ionization energy, what we are doing, we are taking a cation, we are taking a neutral molecule, both with the same geometry, but that is not a physical situation. So, you have something else. Okay. So, if you take out an electron, obviously there will be perturbation, the orbitals will change and they will rearrange themselves. We do not allow that. Okay. So, you get it as I minus A. Okay. In fact, remember that this I minus A plays a very important role in electronic structure calculation also. There is a beautiful paper by Professor Parr and others, where it was shown that this I minus A can be connected to very important quantum mechanical quantities much before. So, this is having another connotation in the totally different area, that's a typical electronic structure calculation. Okay. So in this situation, you can go further approximation. Say for certain systems, even say doing this calculation itself is also very difficult. Then if it is, say, you are doing within Hartree-Fock theory or similar theories, you can apply Koopman's approximation. So this method of calculation, like you calculate En, optimize geometry, with the same geometry calculate En plus 1, En minus 1, like cation and anion, and calculate mu and eta of any given molecule, say your absolute electronegativity and absolute hardness. This is called delta SCF technique. So you will see in the books, they are written delta SCF technique, that means you are doing this calculation. Now, suppose if you do the Koopman's approximation, then I and A, I can write in terms of the HOMO energy and the LUMO energy. Remember, say they give more or less acceptable results in many situations. It is like what is happening in war. In war footing, so main war is being fought by the soldiers in the frontiers. So chemical reaction, if you consider the war between two such reactants, so this is the electron transfer or whatsoever as the frontier. That means HOMO and LUMO, the corresponding electrons, they are taking major part. You can do a simple perturbative treatment and show that their contribution is overwhelmingly large in comparison to the other orbital energies. And this was the theory given by Kenichi Fukui, who got Nobel Prize. This is called frontier electron theory or frontier orbital theory. Okay. So if I do it, then what I get, say I would be, say, energy required to take out an electron, so it would be minus of E HOMO, and this is energy gained if you put an electron in the LUMO. Okay, so this is the minus E LUMO. So I can write down, let's say, the chemical potential. So this one, so this is your A plus I have written, A LUMO plus E HOMO by 2. And chi m is just negative of that. Okay, because I am just approximating using the Koopman's theorem the ionization potential and electron affinity by HOMO and LUMO energies. And similarly, for this, it would be just the HOMO-LUMO gap. So qualitatively, you can estimate that the HOMO-LUMO gap is the measure of the stability of a molecule, because if HOMO-LUMO gap is very large, it is difficult to put an electron or difficult to take out an electron. So you can talk about this at this juncture itself. I am telling you that if you compare the hardness values of some similar type of molecules, the molecule which is having the higher hardness would be more stable. Okay. So this is what is called maximum hardness principle. Okay. We will talk about, I will write down a glossary of this, maximum hardness principle. And also, in fact, we have shown that suppose you think about a physicochemical process, maybe chemical reaction or any physical process like vibration, etc. The favorable direction, like in thermodynamics, you know, for a constant TP process, the favorable direction is one in which the Gibbs free energy decreases. Here also we have shown that suppose you think about a chemical reaction and you go from reactant side to the product side, the hardness increases. So that means not only the stability, even the spontaneity associated with the corresponding direction of spontaneity can be governed by change in hardness. And that is the crux of what is called maximum hardness principle. And there are many such electronic structure principles associated with these quantities. So we could get the global descriptors, because I have to rush a little bit, I have to tell many other things. About the local descriptors, obviously the most important is the density itself. Then you have the Fukui function, and of course you have chi r prime. So here you can see they vary from point to point in a molecule. That's why they are called local. Okay, it is not one constant value for the whole molecule. So we will talk about, let's say, only this one. The other density anyway you are doing in DFT in great detail, and this one I will not touch upon, it's lack of time. So f of r, this is the Fukui function. And why the name Fukui? Because as we will see that here you can explain again the local reactivity in terms of the HOMO and LUMO densities. So Fukui function f of r, you remember what was the definition I had given for Fukui function? You remember this is a cross derivative. Okay. And you can construct some kind of Maxwell's relation considering the homogeneity of the energy. This is same as so the order of differentiation doesn't make much difference. Okay. But what is your del E del V here? This rho, we have already seen this is your rho of r. So that means this gives me del rho r del n at constant V r. What about this? This is del mu del V r at n. So you can see Fukui function, you can write through Maxwell's relations, you can write in two different ways. Okay. So suppose if you want to talk about this del rho del n, the way I did for del E del n, I'll do exactly the same way for del rho del n. Again, VR is constant, so you won't have to change the geometry. You find out the density distribution of the cation and anion and also the neutral one for which the geometry we have optimized, and with that geometry we have calculated the single point calculation for the cation and the anion. So, can you tell very quickly, exactly doing the same analysis, what would be the definition of the Fukui function? Now, here there is slight problem over here. It was there before also. In this case, this rho versus n, this curve is not a continuous curve. As it is not a continuous curve, its left derivative and right derivative, they are different. Okay. So, you can define different types of Fukui functions like f plus r is del rho r del n Vr plus, that means this is plus. So, rho n plus 1 r minus rho n r, it is coming from plus side. Another one I can write f minus r as so this is going like rho n to rho n minus 1. And similarly, I write something like f0 r as half f plus plus half f minus. So, as you can see, this would explain the, at a given point, it's a local quantity, the propensity of the nucleophilic attack. On the other hand, this will talk about the propensity of the electrophilic attack, and this is for the radical attack. So, you can see we are defining three different Fukui functions for identifying three different types of attacks: electrophilic, nucleophilic and radical attacks. Now, what you can do, again, considering that extra electron, whatever you are putting, that is changing the density in that Fukui framework, it is changing the density of the LUMO only, because that is going to the LUMO. And similarly, this is changing the density of the HOMO, because you are taking out the HOMO density. So, approximately you can connect it to the LUMO density, and this you can connect with the HOMO density. That is the approximate form how you can do, and that is the reason why they are called Fukui functions. Okay, because you are making use of the frontier orbitals, frontier orbital densities. Now, if you want to talk about, say, actual chemistry, what we do, we talk about a given atomic site and tell that this atom in this molecule is more prone towards electrophilic attack, but that atom in this molecule is more prone towards nucleophilic attack. So, if you can somehow condense this to the atom, remember, one of the most vague concepts in chemistry is the atom in a molecule concept, but which in chemistry we have been talking about this when you have a molecule that it is attacking the carbon center, it is attacking on the sulfur center, but once the molecules are formed, the atoms, they will lose their identity. And because it's a gray field, big stalwarts, they came and they gave their own definition of atoms in molecules, and accordingly you just simply integrate on the atomic basin and get what is called the electron population. And you get like Mulliken population analysis scheme, Loveday population analysis scheme, Hertzfeld population analysis scheme, and so on. And of course, you get many other population analysis schemes. So, it is of course population analysis scheme dependent, but if you can do this on an atom, then this one will give me some Fk plus, so that is the condensed to atom variant of the Fukui function at the kth atom. And obviously in this case you are integrating it over the atomic basin, so this should be Qk n plus 1 minus Qkn. Okay, similarly this one would be Fk minus, it is not a function of R, it is just a condensed, this is just the number on a given atom. And this one will give you Qkn minus Qkn minus 1 and so on. Okay, so you can see that we are getting the condensed to atom variants of the Fukui function. Now, when we talk about hardness, let us say we are going back and forth between global and local descriptors. So your hardness was del mu del n Vr. Okay, because del E del n is mu, you get del mu del n Vr. Now, if you know the hardness, if you know the chemical potential, say one of the key concepts in the chemical reactivity theory is the electrophilicity. So how do you define the electrophilicity? I am not doing the algebra, it is very simple. I am giving you the hint that suppose you have some free electron C and you put some electrophilic ligand, you place it over here. This electron C is at 0 temperature and 0 chemical potential, and this is having a negative chemical potential. If you put it there in that electron C, there would be change in energy, and that energy change of this would be, say, delta E would be mu delta n plus half eta delta n square. Now, if I see that this del E del n, it will get soaked with the electrons and it will continue till its chemical potential becomes 0. That is the chemical potential of the whole electron C. What is the energy change? That can be obtained from here, and if you want to know the maximum energy change, that would be del mu del E would be minus mu square by 2 eta or minus chi square by 2 eta. So this is considered to be the stabilization or the maximum stabilization due to maximum amount of electron flow when you place the electrophilic ligand in the sea of electron. So this is simple. You put simply d del E del n equal to 0. You get what is the connection, what is the energy you are getting for the maximum amount of electron flow, and that gives you this quantity. So this is the amount of stabilization. So the simplest way of considering that this is a measure of the electrophilicity. So electrophilicity measures the amount of stabilization of the electrophilic ligand when it is placed in some say electron C at 0 temperature and 0 chemical potential. Okay. So this is the electrophilicity index. So omega is mu square by 2 eta. And you can talk about some electrophilicity scale, omega scale, so that you calculate these quantities for various molecules, and then in that scale you can tell whosoever is there above any molecule, that is more electrophilic, whosoever is there below some molecule in that scale, that is nucleophilic, more nucleophilic. Okay. So that means you take a pair and you can immediately determine the which one will behave as electrophile, which one will behave as the nucleophile. Okay. And there are many such papers where they could identify the proper, say, if you do a chemical reaction, which are known as say strong electrophiles, they come towards the top, which are known as strong nucleophiles, they come towards the bottom. So that is verified. So this is more or less acceptable definition of electrophilicity. Now, when we talk about this, there is another quantity generally used, 1 by eta or 1 by 2 eta. This is called softness. So you can see that we are talking about something called softness. So if I consider just the reverse of the hardness is the softness, and you remember this hardness, softness business came into the picture in analyzing general acid-base reactions by Ralph Pearson through his hard, soft, acid-base principle. Okay. So softness from here, if you do, you can see this is del n, del mu, Vr, and I am giving this as exercise. You can write this in chain rules, and you can show that I can define something called a local softness, which is Fr into S. So this softness, again, I can distribute over the whole molecule, or I can go for its Sk alpha is Fk alpha into S, and this quantity will tell you the local softness of a given say atomic site, whether it is prone towards electrophilic attack, nucleophilic attack, etc. And that can be obtained simply multiplying the Foucault function and the softness. Similarly, omega k alpha is Fk alpha into omega. This is what is called philicity, and that can also tell you about the, say, electrophilic attack, nucleophilic attack sites properly. Now, when you talk about the Foucault function, let's say over here, Fk alpha, this is within the molecule. So this is what we call intramolecular descriptor. So if you want to compare, let's say, similar sites in two different molecules, you cannot apply Foucault function. But these are intermolecular descriptors, okay? So which you can, in principle, apply in order to just find out a comparison between, let's say, electrophilic behavior in the similar sites of two different or three different molecules. So you can see there are different variations. So you can talk about intermolecular and intramolecular descriptors. So Foucault function, and Foucault function, as you can see that if you take f of r and integrate, it must give you 1. So it's normalized. Okay. And if you just integrate over here or sum over these, ultimately you can show that your philicity with proper weightage or local softness with proper weightage, they will sum up to the global one. That means whatever the local behavior is there, if you can give proper weightage to them and sum up properly, you must get back the global descriptor. Now in this scenario, let me tell you another thing, say, when we talk about these descriptors, let's say intramolecular or intermolecular various descriptors and associated electrophilic and nucleophilic attacks, there is another, say, important and popular say descriptor, which are derived descriptors, that's called dual descriptor. So this is F2R, this is called F plus R minus F minus R. So you can see that this one or the corresponding condensed to atom variant is Fk plus minus Fk minus this, and this descriptor if you integrate, obviously it will give you 0. Dual descriptor integration over the whole space must give you 0. So in this case you can see, because this is also 1, this is also integrating to 1, so 1 minus 1 must give you 0. The sign of this will tell you, if it is positive, then that site will be preferable for electrophilic attack. Positive means nucleophilic attack. If it is negative, then it would be for the electrophilic attack. If it is 0, then for the radical attack. Okay, this is what is called a dual descriptor. So instead of bothering about the numerical value and comparison with other numerical values, simply looking at the sign, positive or negative, you can talk about these quantities. Okay, I have 15 minutes more.
My job is getting easier.
Easy or difficult? Now, one important thing I must tell you about this local softness. You remember I talked about local softness? This is very important local descriptor. But the corresponding local hardness is an ambiguous concept. I have published only one paper with Professor Manoj Harbola, almost how many? 40 years back. Almost 40 years back, when both of us were postdoc students in Professor Parr's group in North Carolina, Chapel Hill, we published a paper to show that as you can define a local softness, the definition of local hardness is not allowed, in the sense it is ambiguous. You can get any form and all of them are equivalent even so. Okay. So just to take Manoj's name, I am bringing in local hardness concept. Now, suppose if you talk about the spin dependent generalizations of this concept. Okay. So I will just touch upon this because I don't have that much of time. So suppose you have two types of spins. So if I call these as like alpha spin, beta spin, so here you get rho alpha of R, rho beta of R. So let's say our starting point, and let's say n alpha, n beta. If you integrate them, you get n alpha and n beta. That means this is the density of all alpha electrons taken together. This is density of all beta electrons taken together. That means we are talking about spin dependent generalizations of reactivity descriptors. So there are two representations, popular representation. One is NNS VR representation. In this representation, rho alpha plus rho beta is your rho r. This is the standard rho r, what we know. This is called electron density. And rho alpha r minus rho beta r gives you rho s r, which is called spin density. Why I have chosen this specific aspect? Because many people, they calculate spin density, particularly inorganic chemists, without knowing what exactly is spin density. So I am bringing in the concept of spin density here, that you find out, add up all alpha electron densities, get the alpha electron density, and similarly beta, and the difference point to point, you can find out difference, what is at this point, what is rho alpha, what is rho beta at this point, difference. Then you plot, you get what is called the spin density. If you add them, you get the simple electron density, whatever we have been discussing since yesterday. Similarly, N alpha, N beta, this is called electron number. N alpha minus N beta is called spin number. Suppose if I write mu n n, this is del E del n VR ns, mu SS del E del ns, sorry, this is called n, this is called ns, del ns this is called chemical potential, this is called spin potential. Okay. Now this is the way you can find out the derivatives, spin dependent generalizations of the hardness, Fukui function, everything. What?
What is the significance of spin potential?
Spin potential will give you the idea of whenever there is spin transfer. So which side would be more prone towards spin transfer, whether towards this side or that side? Okay, it's not just the electron transfer, it's the spin transfer. Spin transfer means, say, one alpha spin going there or one beta spin coming here, something like this. So there are several reactions where the reaction mechanism requires how the spins are going from one place to the other. It is exactly like chemical potential. Where you talk about the electron transfer, exactly the same. So this is basically a generalization of, I will tell you maybe just a glossary of this. So, but before this, so you can get similarly, sorry, I should write one, mu n and mu s, eta n n, eta ns, eta sn, eta ss. So for hardness you can do this, okay, this type of derivatives like del mu n So if I write del mu n del n ns Vr, so like this quantity is eta n. Similarly, all cross derivatives you can write down. Similarly, the Fukui function also exactly. Del rho del n, you write either the derivative of say electron density or the spin density with respect to spin number or the electron number. So you get all possible derivatives. That depending on your process, you can find out the corresponding derivative Fukui function. These are all spin dependent generalization. There is another representation. This is called n alpha n beta Vr representation. Okay. So here you do everything explicitly in terms of n alpha and n beta. Okay, like mu alpha is del E del n alpha n beta Vr, and accordingly you define other chemical potentials for alpha spin and beta spin separately, or the hardnesses, Fukui functions, all of them can be defined accordingly. Okay. So these are the spin dependent generalizations of the reactivity descriptors, and two popular representations are n alpha plus n beta, this n ns Vr representation, n alpha n beta Vr representation. Now I have 5 minutes left, so maybe. So these reactivity descriptors are best appreciated in terms of their electronic structure principles. I don't have time to explain, but I will at least tell you the names. The first one, of course, Sanderson's electronegativity equalization principle. And there are formal proofs within the CDFT framework of those otherwise qualitatively, say, given electronic structure principles. So what does it say? Say when there is a molecule formation, the atoms with different electronegativities, they will come and there would be electron flow from the atoms with lower electronegativity to higher electronegativity, and until the electronegativity of all those stuff, they will get equalized to the molecular electronegativity, and which can be expressed approximately as the geometric mean of those electronegativities of the atoms. This is Sanderson electronegativity equalization principle or geometric mean principle of the electronegativity. Then you have hard soft acid base principle. See, if all other conditions are same, then hard likes hard and soft likes soft for both their kinetic and thermodynamic conditions. So your hard combination would be preferable than hard soft combination and otherwise. Then I told you already maximum hardness principle. Similarly, there are two corollary principles: minimum electrophilicity principle, minimum polarizability principle, and you have some equalization principles like geometric mean principle, and similarly the hardness and electrophilicity also will get equalized under certain conditions. Okay. There are other electronic structure principles, but in order to appreciate the use of the reactivity descriptors in analyzing the propensity of various chemical reactions, we generally make use of those electronic structure principles. Okay. Or otherwise simple which site is preferable for electrophilic attack and which direction electron will flow, all this stuff, and for which partner the electron flow would be more favorable than the other one. So we can identify the total reactivity pattern and the scenario by making say judicious choice of these reactivity descriptors, both global, local and condensed atom variants. Thank you. If you have any question, tell me.
Anyone has any questions? Yeah.
So when you defined chemical hardness, you defined it as the second derivative of energy with respect to number of electrons. In some literature, I have seen it's actually the half of second derivative of Helmholtz.
Actually, that was the old definition. In order to keep the track with the Mulliken definition that it was I plus a by 2. So it was considered the same footing I minus a by 2. But current day definition is I minus a.
Any other
In fact, the definition of electrophilicity, what I have written mu square by 2 eta, that you will get only if you consider hardness to I minus a.
IP minus A or I minus A, that we also very crudely can use to use as a measure of excitation energy. So I was wondering, how can I think of that to connect it to hardness? Is there any connection
Actually,
between those?
you see, the excitation energy hardness gives you the resistance to the change in the number of electrons. So if you keep the gap larger, so the resistance should be more. That is the standard, say, analysis.
Yeah.
No, that's what I also told the same thing. That if you have, say, homolumo gap is larger, that means it is difficult to take an electron, it is difficult to put an electron. And accordingly, the system is more stable, and that is kind of a corollary of maximum hardness principle also. But I was telling another aspect, this I minus A as another important role which was shown before the conceptual DFT came into being. That was in the calculation, in the electronic structure calculation in those days of PPP models and others. Okay. So the I minus A was identified during that time, the importance of I minus A.
Okay. Thank you very much, Professor Chattaraj. So we started with the perturbation of density as well as the external potential, and we learned so many chemical descriptors. How do we obtain all of them? Thank you very much. I request all of you to join me in thanking Professor Chattaraj for this wonderful lecture.